All right, welcome back. Some more vertical asymptotes, some p.o.d.s, and of course x and y intercepts, like all types of functions. Here we're doing some mixing and matching. Only 3 equations and 3 graphs, so not a whole lot here. But still, we don't know how to sketch any of these graphs. Okay, we don't. The most that we can do is we could do what we've done in the previous section, which is determine p.o.d.s and v.a.s and intercepts, and we can narrow down our selections from there. Okay, so if you look at the functions that are given, none of them are in mapping notation, and if you take a look at the graphs, none of them really look like anything we've graphed before. Maybe graph number 2, and that's the only one, all right? And even that has a p.o.d. in it, so we don't really know how to sketch these graphs. But let's take a look at some bits and pieces of information. And remember, what we've done with these is we would start off by doing some factoring and canceling. So one thing I can do here is I could take function a, and I could start factoring, so I can remove a common factor of x on top, and then I could say on the denominator we have a difference of squares. So notice I can do the factoring, and much like the previous example, we have one factor that cancels and one factor that does not. So that lets us know some information here. Okay, that lets us know we have a vertical asymptote and we have a p.o.d. So the vertical asymptote is the one on the denominator that does not cancel. So that would be the factor x minus 2, that remains there. So if x minus 2 is the factor, then x equals positive 2 is the vertical asymptote. So that eliminates graph 3, which apparently does not have any vertical asymptotes. And there's also a p.o.d. on the factor on the denominator that does cancel. So you can see the x plus 2's do cancel. So we have a p.o.d. at negative 2. Now, we don't know the y coordinate without plugging that in, but I don't even think that's necessary, because if you look at these graphs here, only one of the graphs has a p.o.d., and that would be graph 2, and that p.o.d. is at negative 2, and also a vertical asymptote right here at positive 2. So I believe that we have a match for this. Okay, we can say that equation A goes to graph number 2. Okay, so why don't we take a look at doing the second equation next? Okay, this one's a little different because you notice here that you could factor a 2 out of the top here, but you can't factor anything from the denominator. There's no such thing as a sum of 2 squares, so this doesn't factor. So this would tell us that because there's no factors that cancel, there's no p.o.d., and there's also no v.a., because you cannot factor this down. You cannot solve for x out of x squared plus 1. And of course, the only function here that does not have a p.o.d. or a v.a. is graph 3. So we know that function b matches up with graph 3. And then by process of elimination, we know that equation c would match up with graph 1. Or you could factor it down, and you would see right here that you would have 2x over x minus 2, x plus 2. So you would see right here that nothing cancels, so we would end up having 2 VAs at 2 and negative 2, which does happen with graph 1. Okay, this is another one that you guys can try right here. Okay, you guys can try this one, and you can match these up, and you can see which ones are the correct answers. So I'll get you to hit that pause button right now, and okay, we're back. All right, let's take a look at this right here. Let's see what we have. So once again, okay, you could start with k of x. Doesn't really matter which equation you start with, but this seems like a good idea. Nothing factors on the top. On the bottom, you can factor this down to x minus 2, x plus 1. And because nothing cancels, we know that we have VAs at x is equal to positive 2 and x equals negative 1. And there's nothing that cancels, so there are no points of discontinuity. So of course that would match up with graph 3. So we would say function k and graph 3 are matched up. And then next up, let's take a look at function L. X minus 1 over, okay, that's a difference of squares. We can break that one down. We can cancel the x minus 1s. So what we have here is we have a VA. The VA is from the one on the denominator that does not cancel, which is the x plus 1. If x plus 1 is the factor, then x equals -1 is the VA. And then we have a p.o.d on the one that does cancel. The one that does cancel is x minus 1, so the p.o.d would be x is equal to +1. We could solve for the y-coordinate by plugging it back into the reduced function, but because it's just a mix and match, I don't think it's necessary. You can see that the only one of these three graphs that has both of these characteristics would be graph 1, so this function L would match up with graph 1. And then, of course, we only have one graph and one function left, which would be M and graph 2, so they would automatically match up as well. And from there, okay, you guys can work on page 452, number 4. It's much of the same thing, all right, some mixing and matching, and away we go.